Okay, so let's move to LED drivers for camera flash. So again, just like we have a backlight, it requires white LED, but the current required is much higher. I mean, if you remember, the full scale current in backlight was 20 milliamp only, so one LED. Here, this flash we need much brighter because we are taking a photograph. So the current can go as high as 1 amp actually. Yeah. So and then we know that it has exponential relationship with the forward voltage. So at 1 amp forward voltage require will be more than 3.5 volt, and it could be slightly higher than 3 volt when we are below 200 milliamp or so. So it drives a constant current and operate over the entire battery range. And most of the time, like these flash use 1 or 2 LEDs. So I mean, these days you may find even 3 LEDs actually in very high end phone, but they are like different color LEDs in order to get a more real picture actually. So they mix the color and they change the light color for when they are flashing. So so let's say it's we are having only single LED in this flash. So the way it is done that we have a constant current just like we had in backlight. That was a sink. Here I am showing us source current, and already mentioned that you can have either sink or source depending upon if you have option of using higher voltage. But here the voltage single LED, so voltage required won't be like 28 or 30 volt which we had in backlight. We know the forward voltage is, let's say, 3.5 to 3.6 max. So if I drop to 50 millivolt here, still this voltage output voltage will not be more than 4 volt or so. Okay. So you can easily use 5 volt devices here and live with it. So there is no issue in using high side current source here. But the problem is again we need some dropout voltage for this current source, and there will be power loss. Okay. And then again this current source has to supply as max, I mean as high as 1 amp current, the maximum. So obviously the device size will be much larger here, the power fits which are used in this current source. So we have some efficiency loss here which could be, I mean, 5 to 10%, and not very cost effective because obviously the die size is more. So and your cost is always measured with the die size. So we want to shrink the die area as much as possible. So so what we can do actually, so instead of having this extra current source, we simply sense the current which is going into the inductor. Okay. And we know that so inductor current is what, in case of boost it is I load over 1 minus D, and in case of buck your inductor current is same as I load. Okay. See, if I can sense the inductor current, then I can regulate the load current as well. Okay. So all we need to do just to sense the inductor current, which can be easily done by sensing the current in these MOSFETs, the high side and low side. Okay. And we can estimate the average current based on that. So one thing, so we have two sensors here, and once we sense both the currents, we can add up the two, and that will give me the inductor current. And if I am in the buck mode, then it will be basically same as your load current. If I am in the boost mode, then I have to multiply this by 1 over 1 minus D in order to get the multiply by 1 minus D in order to get the load current, because this will be boosted by 1 over 1 minus D. Okay. So we already talked about different current sensing techniques, if you remember, and we talked about SenseFET, okay, lossless SenseFET, where you have a smaller FET, and so this is your, let's say, 1:1000 ratio. Okay. So if this is let's say 1000 times, this will be only 1 time of that. So this will, and if we match the VDSO, because these devices are linear, we know when it is turned on. So if we do not match the VDS, then you cannot have the same current actually. You cannot mirror the current basically. So instead of 1:1000, the scale ratio, I mean it will be something different. So you won't get the real current number. So we have to match both VGS and VDS in order to get the exact 1:1000 ratio. So once we sense that, then you can dump this current into a resistor, and this V sense will have the information of your current. So your V sense will be nothing but this sense whatever the current flowing into the high side FET divided by 1000, because I have my sense FET is 1/1000 times of this and multiplied by this R sense. Okay. So, and so this is nothing but a regulated cascode in order to match the VDS of these two FETs. So, and but the problem is like it is highly sensitive to the offset and the mismatch between these sense FETs. Okay, and that is why the accuracy may not be as good as what you achieve, let us say, with the external sense resistor, or when you have a series sense resistor with that. And it also requires very high bandwidth amplifier, because it has to track the ramp up and ramp down of the current, where it is a triangular current, not the DC current here, it is AC. Okay, so in order to eliminate the offset, what we do, we use auto zero technique, and we already talked about how you do auto zero, if you remember, again in zero cross detect. Okay, we use, I mean we did that with the inverter, but the concept remains same. So you basically sample the I mean connect in the unity feedback in order to sample the offset, and after that you cancel it, subtract that from your input, and it will get cancelled out. So it is a two phase operation actually. And so as I mentioned, your input offset is stored in say this capacitor, okay, and the next phase it will get cancelled out. So then okay. So the problem here is like you have to do everything in within a very short time, correct. So for the one cycle period, one period of your switching period, you have to do everything, and the next cycle come, then again it's cycle by cycle current sensing. So which means we hardly get any time to basically settle the output. It is quite possible that your output may not get settled, and your next PWM cycle will come again. Okay. So what we do, we use a ping pong in the sense, let us say use a 2 units of this. Okay. So while one is sensing, other you put in the, let us say, auto zero mode, and other is sensing the current. Okay. And when, yeah, no, one is sensing the current, other is cancelling the offset. Okay. So because you need a continuous monitoring of the current here, and the offset cancellation happens in one basically phase you sample, other phase you cancel the offset, but here we require a continuous monitoring of the current. So you cannot put this in the auto zero mode, okay, otherwise you will miss the current.
Phase 1 of one unit is phase
Yeah,
of the other unit.
yeah. So it's like that. So when this other guy is sensing, you keep the let us say second guy in the auto zero mode, and then you reverse the basically role in the next cycle, and that is what you keep doing. That is why we call it ping pong actually. So in that manner you can do continuously monitor the current as well as cancel the offset. Okay, so it improves the matching, but will slightly yeah. So this offset cancellation, obviously, as we talked about, it improves the matching because we are cancelling the offset, so accuracy will be higher. So one more thing we need to remember that this ratio of this FET 1:1000. So if you use a, let us say 1:100 into instead of 1:1000, then the matching between these two devices will be better. But the problem will be, let us say this guy is carrying 1 amp of the current, 1:1000 means this is carrying 1 milliamp current. Now if you make 1:100, then your sense FET has to carry 10 milliamp of the current. So and more current you have in the sense FET, it's I mean this current is completely lost, you are not utilizing this current because it is getting dumped into the resistor. So, we are losing 10 milliampere there. So, in order to basically improve the accuracy, we have to sacrifice the efficiency here by increasing the size of this sense FET. So, let us see how we can improve the accuracy without degrading the efficiency. So, I can still let us say make this 1:10, 1:1000 ratio. Let us say I have a 10 devices of same size. So, if I connect all the 10 in parallel, then I will get 1:100 ratio. But instead of doing that, what I will do, I will turn only one unit at a time, okay. But in one period, I will move across all the FETs, correct. So, let us say your one clock period is 1 megahertz, frequency is 1 megahertz, which is 1 microsecond, and I switch these FETs, turn on and off these FETs, let us say at 10 times. So, and I have a 10 of these. So, in one clock period I can cover all the 10 FETs. So, I turn on one, sense it, okay, for 1/10 of your period. Next, let us say 1/10 period, you connect the next one. So, similarly you rotate through all the, it is similar to dynamic element matching what you do in people who know the ADCs, they will understand better. So, so what you are doing actually effectively, you are moving through all the FETs, and these FETs are in order for better matching, they are scattered or spread all over the places within your bigger power FET. Okay. So, let us say let me just draw here. So, if this is my main FET, okay, and this main FET is consist of like a multiple units, it won't be like a single. So, and then my sense FET is very small. So, let us say I mean, and my sense FET, let us say I have a single unit which is lying here. So, it is very hard to match this the condition at this corner to here. So, what we do, if you are using multiple FETs, we can spread it out all over the places, and when we cover all the, let us say, sense through all the FETs and take the average. So, ultimately what you are doing, you are improving the matching, and you will get much better accuracy compared to what you get with a single unit of 1:1000, and without this, this is done without increasing the current, because I am turning only one FET at a time. So, that is advantage actually. Okay. So, rest of this is, I think we are running out of time. So, I mean how you after sensing how you scale. So, you are multiplying by 1 minus D boost ratio, and this is how we are doing it. This is your chip. I do not think we need to talk about chip here. So, it's okay. I think main thing I want to show here, improvement in the efficiency, because we do not have that current source. So, you can see at 3.2 volt when we are mostly in the boost mode 13%, and in the buck mode you are 6%. So, 4.5 to 13% improvement in the efficiency you are getting. Okay, this is accuracy plus minus 2.8% at different current levels. So, and most of the time the accuracy requirement is like less than 5% or so. So, it is within the range.